Hi, everybody. Welcome to our second online lecture. Today's lecture is for Monday, March 23rd, 2020, recording it a little bit early. A couple admin things. So homework 7 and in class 7 were officially assigned on Friday's lecture on March 20th. The solutions to homework 7 will be posted online. In class 7, I'll post that after you submit it on Friday, but please use these online office hours to work on that. You can collaborate with classmates, hopefully using the Google Hangouts link. You can also ask me questions. So it would be great to use online office hours for working those problems. Exam 2 is likely going to evolve as we get more information about the developing situation with our online classes. I'm not sure. I think right now the plan is for everyone to be back in Bancroft by April 1st. If we are still online, my tentative plan is to post exam 2 on Blackboard. It'll be available for 24 hours. So I'll post it early in the morning on April 1st, and it'll be available until April 2nd. Please make sure you submit it within 24 hours of April 1st. If it's online, I think it makes sense to make it open note. We also have a lot more equations that we have to be thinking about, especially with API design guidance. So okay to make it open note, but please do keep in mind that while I love collaboration on homework and in-class problems, the exam should reflect your individual work. So please keep that just to yourself. You are, though, obviously always welcome to ask me questions via email or text, especially when those questions are to clarify what I want you to solve for. So definitely feel free to ask me questions. That's my phone number, so feel free to shoot me a text if it's something urgent. And I'll post last year's exam on Blackboard. I'll have that posted by today in the exam folder in the course materials tab. Just keep in mind that since we are sort of an online format, I'll try not to increase the length by too much, but I might kind of change up the format a little bit, especially with our revised course policy. One other quick update I wanted to let you know, I was trying to get VPN access for us to be able to use the STAD program off the yard. It looks like our class didn't quite make it into a top priority. I think they prioritized some of the first classes that required VPN access. So our course policy has changed. Please check out the revised student learning objective. We've changed it from using this program a little bit more often than to just being familiar with the program. So we had some introduction to it with the homework. You guys did a good job on the homework, and I think just being familiar with the program and the process is going to have to be our new course policy, sort of given these new circumstances. Please let me know if you have questions about that. Anyways, getting down to business, last time we talked about the API design criteria. We did a bit of an introduction lecture, and we started our design check. We completed our axial check, and so if we're following our bracketology, we had column against the axial check. Since our actual stress was less than our allowable stress, our column advanced, and now we have to complete the bending check, the shear check, the hoop stress check, and the combined stress check. So just as a bit of a refresher, and I'll post sort of these combined notes to today's lecture. So here was our example problem. These are the notes from last time. And we just want to check that this column satisfies API design criteria. We have these loads. We have a 50 kip axial load, a 250 kip foot moment, some lateral loads, maybe due to a current or something. The first thing we always have to do is we have to use statics to find our maximum shear, maximum axial load, and maximum moment. Then we can step through our axial compression check. That starts with finding the effective length. All of this is to find our critical buckling stress. We find the slenderness ratio. With some other parameters, we can check whether there will be local buckling. And then we can find C sub C and compare that to our slenderness ratio. Since our slenderness ratio 151.6 is greater than C sub C, we have an Euler column, a long skinny column. And we can then calculate our allowable stress based on a modification to Euler's equation and compare that to the actual stress, which is just our maximum compressive load divided by our cross-sectional area. We have an actual stress that's much less than our allowable stress, so our design checks out and we can move on to bending. All right, so let's go ahead and continue. So I'll get rid of these notes. And here we are with step 3. Which is our bending check. And here we're going to compare our allowable bending stress capital F sub B to our actual bending stress or lowercase f sub b. So again, in general, our allowable stresses are going to be shown in capital letters and our actual stresses are going to be in lowercase letters. The first thing we need to do is to check the ratio D divided by T times Fy. So plugging in numbers from our example, our column outer diameter was 48 inches, our thickness was 1 inch, and our yield strength is 50 kips per square inch. So when we calculate that, we have 2,400 KSI. There's 3 scenarios based on this ratio of how we'll calculate our allowable bending stress. So we have 3 options. The first is if D over T times Fy is less than or equal to 1,500. Then we have our allowable bending stress is equal to 0.75 times Fy. It's not our case, but we'll include it for completeness. If we have 1,500 less than or equal to D over T times Fy is less than or equal to 3,000. Then we have our allowable bending stress, capital F sub B, is equal to 0.84 minus 1.74 times Fy D over T. So again, that ratio, and then also divided by E. That whole quantity times our yield strength, excuse me. And so this is our situation. Let's, for completeness, add that third equation. If your ratio D over T times Fy is greater than 3,000, and note, you also must have D over T less than or equal to 300 for this circumstance. If D over T is greater than 300, you need a new design. They're saying that's really not going to withstand the necessary bending. And if that's the situation, we have our allowable bending stress is equal to 0.72 minus 0.58 times Fy D over Te. That whole quantity times Fy. So again, our column is in case 2. So we have our allowable bending stress is equal to 0.84 minus 1.74 times D over T times Fy is 2,400. That's D over T Fy. And then we need to divide this value by E. So divided by 29,000 KSI times 50. KSI is our yield strength. So we have an allowable bending stress equal to 34.8 KSI. Okay, so that's that step. Next, we have step 3.3, which is to find our actual bending stress. Much quicker to find your allowable bending stress than your allowable axial compression stress. At any rate, our actual bending stress, which is lowercase f sub b, this is equal to our max moment times our outer diameter divided by 2, all divided by the moment of inertia. So plugging in numbers, I can look back to our first step. Our maximum moment from summing the moments was 1,762.5 hip feet. Remember to be careful with your units. Since D is in inches and I is in inches to the 4th power, let's convert this to inches to kip inches. So times 12 inches per foot times D over 2 is 48 inches over 2, all divided by our moment of inertia, which is 40,789.7 inches to the 4th. We found that in step 2.1.2 when we found our radius of gyration. And so then our actual bending stress is equal to 12.4 KSI. All right, the last step for bending, 3.4, is to check if your actual bending stress is less than your allowable. We have 12.4 KSI, which is less than 34.8 KSI. So, okay. So we can put a big check mark here. If you want to, you can go back to sort of the beginning here and we can move our column right along because we passed our bending check. Next, we're going to move on to our shear check. So this will be step 4. Our shear check. And again, we're comparing the max allowable shear stress, capital F sub V, to our actual shear stress, which is lowercase f sub v. This is a pretty quick check. Your allowable shear stress, capital F sub v, will always equal 0.4 times Fy. We have Fy is equal to 50 KSI. So our allowable shear stress is equal to 0.4 times 50 KSI, or our allowable shear stress is 20 kips per square inch. And next we'll calculate the actual shear stress. So we have our actual shear stress, step 4.2, or lowercase f sub v, is equal to your maximum shear. Again, this is from step 1, divided by 0.5 times your cross-sectional area. So again, if I look back into step 1, we can see that our maximum shear is 18.5 kips divided by 0.5. And again, our area comes when we're calculating the radius of gyration in our axial compression check. That's 147.7 inches squared. Just for completeness, I'll add this is step 2.1.2 when we're calculating the radius of gyration and our actual slenderness ratio. Plugging these numbers into my calculator, I get that my actual shear stress is equal to 0.25 KSI. All right, so that last thing is just to compare. So step 4.3, we check FV lowercase is equal to 0.25 KSI, which is indeed less than 20 KSI, which is equal to our allowable shear stress. So we can continue. Again, just for completeness, I'll go ahead and move this right along in my bracket off the page, but I just wrote down that our column passed the shear check with lowercase f sub v less than capital F sub v. So next up, we have our hoop stress check. And I mentioned this briefly last time, but hoop stress is a stress that's due to an internal or external pressure acting over an entire surface. So in this case, it's hydrostatic pressure. Let's go ahead and define that briefly. So step 5 is our hoop stress. Check. The first thing we'll do is define where we have hoop stress is stress due to internal or external pressure acting over the surface of a body. Important for hydrostatic pressure on underwater structures. So we definitely have to think about this. Take a moment and think about where would hoop stress be the worst if we're thinking of it as a function of hydrostatic pressure. That would be where your hydrostatic pressure is the maximum, so at the bottom of the cylinder. So we have hydrostatic pressure is max at the seafloor. So how do we calculate this? The first thing we do is we want to find our elastic hoop buckling stress. Or F sub HE. This is equal to 2 times the hoop coefficient that we'll talk about in a second, times the elastic modulus, times your thickness divided by your outer diameter. Defining terms, we have E is equal to elastic modulus. T is equal to thickness. D is equal to your outer diameter. And C sub H is a coefficient based on geometry. So let's go ahead and calculate that. I'll slide this page up. A little bit. Great. And so the first thing we do to find our C sub H, this hoop coefficient, is we have 5.1.1. And we'll check our M parameter where m is equal to our length over our diameter times the square root of 2d divided by t. As a note, keep in mind this is the actual length. So effective length only comes into play when you're calculating axial stress, axial compression. So plugging in numbers here, I have 100 feet is the length of my column times 12 inches per foot, because my diameter is in units of inches. Alternatively, I can convert my diameter into feet, but let's keep everything in inches. So we have 48 inches. Good, my units will cancel. Times the square root of 2 times 48 inches divided by my thickness is 1 inch. And so I have m is equal to 245 unitless. The next thing I do is I compare m over d over t. So this is equal to 245, we found here, divided by 48 inches over 1 inch. So 245 over 48 is equal to 5.1. And based on this ratio, we have 5 different scenarios. So I'll show you quickly in the Cliff Notes. This is going to be page 3 of the Cliff Notes. So if we have m greater than 1.6 d over t, we can move this d over t here. So m over d over t greater than 1.6, that's our case. We have ch is equal to 0.44 times t over d, and then 4 other scenarios with 4 other equations. Let's put these equations in the notes just for completeness. So with 5 scenarios, the first scenario, we have m over d over t, which is greater than or equal to 1.6. This gives us c sub h is equal to 0.44 times t over d. Since this is our column, we can plug in numbers here. So we have 0.44 times 1 inch over 48 inches, which gives us 0.00917 is going to be our value for c sub h. If, though, I have m over d over t is greater than 825, m over d over t, which is less than 1.6, then I have a new equation. I have c sub h is equal to 0.44 times t over d plus 0.21 times d over t cubed, all divided by m to the 4th. So these are empirical relationships based on testing, observations, and things like that. My third case is that if 3.5, so just the quantity 3.5 is less than or equal to m, so no longer divided by d over t, is less than 0.825. Here's d over t, so sort of this scenario here is my upper bound. Then I have c sub h is going to equal 0.736 divided by m minus 0.636. Case 4 is if 1.5 is less than or equal to m is less than 3.5. I have c sub h is equal to 0.755 divided by m minus 0.559. And then finally, if m is less than 0.8, or sorry, if m is less than 1.5, we have C sub h equals 0.8. All right, again, we had the first case scenario, so we've already calculated our hoop coefficient. Plugging in numbers, we can say, therefore, F sub HE is equal to our hoop coefficient, so 0.00917 times 2, so 2 times C sub H, times 29,000 KSI, times 1 inch over 48 inches, or F sub HE is equal to 11.08 kips per square inch. Once we have our elastic hoop buckling stress, we want to calculate our critical hoop buckling stress. So we check critical hoop buckling stress, which is F sub HC. And again, the first thing we want to do is compare F sub HE, so our elastic hoop buckling stress, to our yield strength. So check F sub HE over Fy. For our beam, this is 11.08 KSI divided by 50 KSI, which is equal to 0.22. There's 4 possible scenarios based on this ratio. So we have 4 scenarios. The first is if F sub HE is less than 0.55 F sub Y. This is our case. If we put F sub Y over here, this is 0.22 is less than 0.55. This tells that we will have elastic buckling with F sub HC equals F sub HE, which is equal to 11.08 KSI. Again, this is the scenario that we are in with our column. For completeness, let's go ahead and finish the other 3 scenarios. So if we have 0.55 times Fy is less than F sub HE, which is less than or equal to 1.6 Fy. This will give us inelastic buckling. And we have F sub HC is equal to 0.45 times our yield strength plus 0.18 times our elastic hoop buckling stress, F sub HE. If I have 1.6 times my yield strength is less than F sub HE is less than 6.2 times my yield strength. Again, I have inelastic buckling, and F sub HC, my critical hoop buckling stress, will equal 1.31 Fy divided by 1.15 plus Fy over F sub HE. And then finally, my last case scenario, if F sub HE is greater than or equal to, oh, sorry, equal to sign is here. This is just greater than 6.2 times Fy. We have inelastic buckling with F sub HC equal to Fy. All right, we have our critical hoop buckling stress. The next thing we need to do is find our actual hoop stress. So find actual hoop stress. lowercase f sub h. This is equal to my hydrostatic pressure times my outer diameter divided by 2 times my thickness. So again, we're relating that hydrostatic pressure to the surface of the body. Again, P here is equal to hydrostatic pressure, which is equal to rho GD, or the unit weight of water, gamma W times D. Here we have gamma W equals unit weight of water, which is equal to 62.4 pounds per foot cubed for fresh water, or 64.0 pound per foot cubed for salt water, approximately. And D is the same D from waves, that's your depth. And if this is in pounds per foot cubed, this should be in feet. And then our pressure would be in pounds per feet squared. This becomes a bit of a exercise in unit conversion, just because we have inches, pounds per feet squared, and we want it to be in kips per square inch. So calculating my actual hoop stress, I have pressure, so I have gamma W, so 64 pounds per foot cubed, times my depth is 100 feet. That's the from the problem definition. Let's convert this to pounds per inches squared and then kips per inches squared. So we'll multiply 1 foot squared is equal to 144 inches squared. And then we have 1 kip is equal to 1,000 pounds. So I'm crossing off pounds, I'm crossing off feet squared, feet cubed, and then I have kips per inches squared. So that's my pressure times my diameter is 48 inches. Dividing that quantity by 2 times 1 inch. So I get F sub H, lowercase f sub H, is equal to 1.07 kips per square inch. And the last thing we do, this step is actually slightly different than other steps. We have step 5.4, is we check that F sub H is less than F sub HC, our critical hoop buckling stress, divided by a factor of safety. So Fs is equal to factor of safety, which is equal to 2.0 typically, or 1.5 for special or extreme scenario. So maybe if you're designing for something like a hurricane event, you might lower your factor of safety because you're already anticipating very high loads. Let's use a factor of safety of 2. This is just a normal condition. So we have lowercase f sub h, our actual hoop stress, is equal to 1.07 KSI. Let's see if that is less than 11.08 KSI over 2, our factor of safety, which is equal to 5.54 KSI, equals FHC over FS. Yes, it does. We have 1.07 is less than 5.54. So, okay, and continue. Great. So we can go ahead, and our column has passed the hoop check 2 with F sub H lowercase less than our critical hoop stress over a factor of safety. Sorry, I was off the page. So we have our column passes this hoop stress. The very last thing we have is our combined stress check. So let's go ahead and finish up this problem. So the very last thing we need to do is step 6, our combined stress check, which is combined stress check. And specifically, we consider axial compression and bending. And so we need to consider effects of combined loading. So if you have a large compressive load, so a large P max, or another way to say this, if your actual axial stress divided by your allowable is greater than 0.15, you may cause the member's axis to deviate from its line of action. So basically the axis, because it has such a heavy load, will sort of shift slightly to one side or the other. So deviate from the line of action of the vertical compressive load. So basically another way, if I drew this, here's my column with some load P. If P is large enough, here's the line of action of my column. Here's P. But what my column does is it bows slightly to the side because I'm pressing down on it so hard. And this distance we call delta or deflection. And this will cause additional bending in addition to the bending that you already have due to lateral load. So this causes additional bending. And this is called the P delta, or P, this is the Greek symbol for delta, effect. So the first step we have to do is 6.1, which is to check that lowercase f sub a over our capital F sub a is greater than or less than or equal to 0.15. So for our column, we have our actual over our allowable axial stresses are equal to 0.339 KSI. This was from step 2. Also from step 2 is our allowable, which is 6.5 KSI, which is equal to 0.52, which is less than 0.15. So we do not have a P delta effect for our column. So therefore, we have no P delta effect and just one combined stress check. Which is to check that the ratio of our actual to allowable axial stresses plus the ratio of our actual to allowable bending stresses, sorry, this is a B, is less than or equal to 1. So plugging in numbers here, we already calculated, sorry, this is 0.052. 0.52 is greater than 0.15. Plugging in numbers though, we have 0.339 KSI over 6.5 KSI, plus looking back at step 3, we found that our actual bending stress was 12.4 KSI divided by our allowable was 34.8 KSI. This is going to equal 0.41, which is indeed less than 1, so okay. And our beam satisfies all requirements, which implies that the design is safe. And this is our answer. Very quickly, I do want to point out there's two other situations that you could have considering the P delta effect. So what if we found that our ratio was greater than 0.15? So if lowercase f sub a over capital F sub a is greater than 0.15, the P delta effect may be significant. So we have two checks. The first is that the ratio of your actual to allowable axial stresses plus a coefficient C sub m times your actual bending stress divided by 1 minus F sub a over F e prime times F sub b is less than or equal to 1, where here we have C sub m is equal to 0.85. Always, that's a coefficient. And F sub e prime would be your allowable bending stress for, or sorry, your allowable axial compression stress for an Euler column. So this is what we have, but the equation is 12 over 23 times pi squared E over your slenderness ratio squared. The second check you have, if the P delta effect is important, is that the ratio of your actual compressive stress to 0.6 times your yield strength plus the ratio of your actual to allowable bending stresses is less than or equal to 1. You must satisfy both requirements. And then finally, note one more special case. If you have a pile driven into soil subject to lateral and axial loads, we use the following equation instead. And I'll be very clear if you have this special case. I'll probably say, if you have a special case where this pile is driven into soil subject to lateral and axial loads, and then you would have to use this check instead, which is your actual compressive stress divided by 0.6 times F sub xc. This is your inelastic local buckling stress, which you find in step 2.1.3. So you've already found this, it's just a matter of going back and finding that value, plus F sub b, lowercase over your allowable capital F sub b. You have to check that that's less than or equal to 1. And once you've satisfied all of these checks, as we have, we can go ahead and set our column and say that it is safe. And so that's sort of your final answer, but you have to clearly show that it passes each of these checks in order for an engineer, a client to understand that the pile is indeed safe. That's all I have for you guys today. Next time we'll do another example, just going through the whole process without some of this anecdotal explanatory information. I hope you guys are having a great day and looking forward to seeing you all soon.